models. We're going to go through a bunch of different models that can happen that have exponential functions involved in them. So I think this was a part of the 3-1 notes that you were listening to for homework. Okay, guys, quiet, please. So if a population P is changing at a constant percentage rate each year, then we call it exponential, and it will look like the following model. So we would have the function P of T is equal to your initial, which we're going to use as a P with a subscript of 0, P naught, times 1 plus R, where R is your rate to the T. So P sub 0 is your initial population of whatever it is we're talking about. R is your rate expressed as a decimal. And sometimes students will mess that up because if your percentage is like 0.8%, you need to make sure you convert it to 0.008 for your decimal. And T is in time, in years. Okay, so if your R is bigger than 0, then we say that we have a growth factor of whatever 1 plus R is. So if that base of our exponential model is larger than 1, then we know that it's growing, and it will have a growth factor of whatever R plus 1 is. If my R is smaller than 0, then it would be 1 minus a negative, which would get me a number smaller than 1. Then we would call that the decay factor, which means that it's decaying. It's getting smaller for the population. Okay? All right, so for example 1, tell whether the model is growth or decay, and then find the constant percentage rate of growth or decay. So here we've got A serve side P of T is equal to 100,000 or 102,324 times 1.025. What I really care about is this number here, bigger than 1, so that means that we have growth. So 1 plus R is equal to 1.025. So what does my R equal? 0.025, which is what percent? 2.5% would be how much you're growing by. For B, 0.92 is smaller than 1, so that means we have decay. So that means that 1 plus R needs to equal to 0.92. Well, actually, I guess it would be 1 minus R, sorry. 1 minus R is equal to 0.92. So we can either think, what am I subtracting from 1 to get to 92, or solve it out. That would get you negative R is equal to negative 0.08. So R is equal to 0.08, which is the same as 8%. Do you need to do the algebra? Probably not. If I can just think in my head, what am I taking away from 100 to get to 92? 8%. What am I adding to 100 to get to 0.025? 0.025. Okay, so can you determine whether there's growth or decay in an exponential function? Yeah? Okay. Example 2. Now we're going to come up with an actual function given some value. So determine the exponential function. Initial value is 12. So that means we're going to have a 12 times 1 plus something. We are increasing at a rate of 6%. So I'm going to add 0.06 to the t power. So P of T is equal to that. And I could just simplify that number inside the parentheses to 1.06. So there could be my function. Do not ever distribute that 12 to the 1.06 because you have that exponent of t. You can't distribute it through. It doesn't work like that. Bad math. Okay, good with the first page? All right, so now let's start doing some solving. So example 3, suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 250,000. Okay, so if we are doubling, what should be my growth rate? Well, so it would double by 100%. So that number inside your parentheses would just be 2, right? That would be your growth rate or your growth factor. All right, so we're doubling every hour. We're starting with how much bacteria? 100. So there's my P naught. All right, so P of T is equal to 100 times 2 to the T. And then we want to predict how much bacteria, or when the bacterial will get us up to 250,000. So I'm gonna input this in place of my P of T, because that would be my output. And we need to solve for what T gets us to that as our output. So plugging in 250,000 on the left. Now we have an equation that I know you guys can solve. I take out my zeros out of 100. Then we've got 2500, so 2500 is equal to 2T. Logs of both sides. So then it would be whatever the log of 2500 divided by the log of 2 is. Is it about 11.287? Log of 2500. What's the last decimal? I only have 3 decimals here. 2877. So 11.2877. What's T in hours? So after about a little over 11 hours, we would have our bacteria up to 250,000. Okay. All right, so now let's do some radioactive decay. Oh, really quickly, if we wanted to use our calculator, it says to show it graphically. We didn't do that. If I want to use my calculator to do it, how do we type this into our calculator? Everybody can do that? Get my calculator out. Where are you, calculator? I can't use my left hand. So I would be under y equals. I could type in my function on the right, which is 100 times 2 to the x. And then I could type in my function on the left, which is just a horizontal line at 250,000. If I went to just a zoom 6, I'm not going to see it because that's just a 10 by 10 grid. I need my y to get up to a y max of maybe like 300,000. Enough zeros. Ooh, doesn't like it. All right, let's see. X min. Oh, because I have it at the min. Oops. 0. Y max. Whoa! What was that? What was that? Carter did something?
Yeah, that was me.
Did something fall off?
I don't know. We just want to blame him.
Oh, I still can't see it, so I got to move over. My X max, let's put that at 100 maybe. All right, there we go. We see the intersection? So my intersection should be my answer. So intersect. There it is. 11.2877. So we could do it on a graphing calculator if I wanted to check my results. Right? So if you just wanted to make a quick sketch of that on your graph. Right? So your intersection of the two lines would be your answer. So 11.2877, comma 250,000. Okay? So use those graphing calculators to your help to make sure you're getting correct answers. Okay, half-life, decaying. So it says, suppose the half-life of a certain radioactive substance is 40 days, and there are 8 grams present initially. Find the time when there will be 1 gram of substance remaining. Okay, so we're starting out with 8. So P of T is equal to 8. And if I'm taking a half-life each time, my decay rate would be a half, or 1 minus a half, which is a half. And then here's the tricky part. T represents time in years, but we're doing a half-life every 40 days. So I'm going to take my years and I'm going to divide it by those 40 days. So that means every T over 40 is when my half-life is going to be occurring. Okay, and then we need to get to 1 gram. So I'm going to plug in 1 on the left side. So 1 is equal to 1/2 T over 40, which is the same as 1/8 equals 1/2 T over 40. Take a log. You could take a natural log on both sides too. You would get the same answers if you did a natural log on both. So on our calculator, we're going to do a log of 1/8 divided by a log of 1/2 is equal to T over 40. So then I could just multiply by 40 on both sides. So I'm going to do all that jazz on my calculator. Log of 1 divided by 8 divided by log of 1 divided by 2. Hit enter, multiply by 40. I get 120 days. Is when it would eventually get down to just 1 gram from 8. If it halves itself every 40 days. Okay? All right. Uninhibited growth of cells. Have you guys hit any of these things in any of your science and chemistry class? Or biology? I don't even know where you would hit this. All of this makes sense. The last time I had a science class was freshman year of college. Okay, so your formula for uninhibited growth of cells formula is A of T is equal to your initial, which we're going to use as A naught, E, K to the T, where K must be positive. So K represents the growth rate of your cells, and it must be positive. So, for example, 5, it says a culture of bacteria follows the law of uninhibited growth. So that means I need to use that formula. If 500 bacteria are present initially, and there are 800 after 1 hour, how many would be present in the culture after 5 hours? So, first and foremost, let's figure out what our formula would be. So it would be A of T is equal to, what's my initial? 500 tells us is the initial. And then it would be E to the K times T, which in this case, it's telling us that after 1 hour, so K times 1, I'm at 800. So let's solve that for K. So dividing out 500 on both sides gets us 8/5 is equal to E to the K. Because I have an E, I can take a natural log of both sides. The natural log of 8/5 is approximately 0.4700. So now, my original model is complete. So A of T is equal to 500 E to the negative 0.47T. I'll eliminate those zeros. It's now evaluated at 5. So A of 5 is equal to 500 E to the negative 0.47 times 5. I'll help you out. It is about 5,242 bacteria. Yes, sorry. I don't know why it's negative. It's not supposed to be negative. Just erase it. The answer is correct with it being positive. But let me check to make sure. 500 times E to the 0.47 times 5. Yeah, I don't know why I put a negative there. Good catch. Okay, so then for part B, how long will it before the culture contains 200,000? So now we're going to use this and plug 200,000, or not 220,000 on the left-hand side and solve it out. So we get 20,000 is equal to 500 e to the k t. Oh, nope, we know k is 0.47 t. So 20,000 divided by 500 gets us 40 is equal to e to the 0.47 t, natural log. So we're going to do the natural log of 40 is equal to 0.47 t divided by 0.47. So then on my calculator, we would do the natural log of 40. Divide that by 0.47, and we get about 7.8487 hours. What does 0.8487 hours look like in minutes? How would I figure that out? Just multiply it by 60. So is it about 51 minutes? Is that what it is? So really it's about 7 hours, 51 minutes is when our culture will get to 20,000 bacteria. Okay? All right, almost there. Calculators, can you do a regression on your calculator for exponentials? Get your calculator in hand. Make sure you can do that. Do we remember how to come up with any type of regression model? What we have to do first. How do I enter that table of values into my calculator? Yeah, stat edit. So we hit the stat button, go into edit, clear your list by highlighting L1, hit a clear enter, highlight L2, hit a clear enter, and then we'll put our weeks in L1, so 0, 1, 2, 3, 4, 5, 6. We'll put our weights in L2 for our Ys, 100, 90.4, oops, didn't like that, 76.8, 69.7, 58, nope, 0.2, 49.7, 44.2. And then how do we get to the regression options? Hit stat again. Go over to calculate. And then 4 through 9, 0A, they all have regressions attached to them. Which one do you think we're going to pick here? No, we don't want linear. We don't want quadratic. We don't want cubic. We don't want linear. Yeah, so exponential is going to be the one where we're going to go to. So hit that 0. My X was my list 1. My Y was my list 2. We could store it if I wanted to, but I'm just going to hit enter. And we get the following results. Did you guys get the same thing as me?
I didn't get the R squared.
Oh, that's okay if you didn't get the R squared. That just tells us how strong our model is. We'll do that for stats if you ever get there. Okay, so our equation is for A. Let's rewrite this. So Y is equal to 102.3061 times 0.8693 to the X. Nope. Go away. All right, so there's our equation. I write it here. So Y is equal to 102.3061 times 0.8693 to the X. So now, for B, what's the half-life of the radioactive material? So how could I figure out the half-life when that happens? So at what point in time does my initial get to half? Well, what is half of my initial? Well, instead of doing math, can we just think about whatever this number is, when I would divide this out, wouldn't it just take me to half? So can I just go right to 0.5 is equal to 0.8693 to the x? Right, because if I were dividing it out, it should get me to half, because I want it to be the half-life. Okay, let's log both sides and divide it out. So the log of 0.5 divided by the log of 0.8693 gets us x is approximately 4.9487. What are we in? Weeks? Is where we'll end up about halfway there. For part C, we're going to do the same thing for 10. So set 10 on the left. Can I erase this? We're okay? So C, we're going to put 10 on the left. So 10 is equal to, oh, I'm writing really small. 10 is equal to 102.3061 times 0.8693 to the x. Divide this out. Divide that out. 3061. So 10 divided by 102.3061 is about 0.097745. I'm just going to leave that on my calculator because then I'll do a log of that and divide it by a log of the 0.8693. So log second negative gets you your last answer. Divided by log of 0.8693. It's about 16.6019 weeks. This is when we would be about at 10. And then how much radioactive material would be left after 52 weeks? Well, we would just evaluate our function with x being 52. So what is that? 102.3061 times 0.8693 to the 52nd. So I forget what we had. So P of 52 would be approximately 0.0703 grams. We didn't use a letter for our function, did we? I think we did. Okay. Almost there. Last one. Okay, so here we have these carrying capacity functions again, where we have horizontal asymptote maxing out at 1,500, and then we're bottomed out at 0. So it says Surfside High School has 1,500 students, Max, Patty, Juan, and Andrea start a rumor, which spreads logistically so that there's our function, models the number of students who have heard the rumor by the end of t days, where t equals 0 is the day the rumor begins. To find how many start it, S of 0 would be equal to 1,500 over 1 plus 38e to the 0, which is just 1. So really we're doing 1,500 over 39, which is about 38 students. So that means we start it with 38 students with the rumor. Those 38 students, my goodness. And then for part B, how long does it take to get to 1,000 students? So we're going to plug 1,000 on the left. So 1,000 is equal to 1,500 over 1 plus 38e to the negative 0.9t. So rules of proportions, I can just switch this. So I get 1 plus 38e to the negative 0.9t is equal to 1,500 over 1,000, which would just go to, what is that, 5 halves? No, take out 5, 3 halves. So that whole right side becomes 3 halves. Then what can we do? Subtract 1. So 38e to the negative 0.9t is equal to 3 halves minus 2 halves is 1 half. What's your next move? Divide out 38. So e to the negative 0.9t is equal to 1 over 76. Natural log both sides. So then you get negative 0.9t is equal to whatever the natural log of that is. Natural log of 176. It's like negative 4.3307 and some change. Divide by negative 0.9. Gets us about 4.8119 days. Are we in days? Days. So by day 5, 1,000 students have heard the rumor. Terrible students. All right.